I welcome you all for this today's webinar on an introduction to CFD, that is Computational Fluid Dynamics. Let me introduce our today's speaker, our today's guest, Mr. Sandeep Hirde. Okay. Mr. Sandeep has done his MTech, that is Master of Technology, in Heat Power Engineering, that is from thermal side, from VNIT Nagpur. He has experience of more than 14 years in the CFD, that is Computational Fluid Dynamics area, in some of the very reputed companies. He has worked in the companies like GE India, that is General Electric India Technology, Schneider Electric, and Senvion India Private Limited. Currently, he is working with Siemens Gamesa Renewable Energy Bangalore as a CFD technical head. About his achievements and awards, let me tell you, he has been given an Internal Trainer Community Award for top trainer in all over India by Schneider Electric. He has 3 patents on his credit. He is a certified DFSS 6 Sigma with green belt. He has also presented papers on CFD simulation in 2 international conferences organized by ANSYS. So, friends, today we have with us such an eminent person in the area of CFD. As you know that in this current situation, the importance of simulation, okay, especially for the final year projects, the simulation area is upcoming field for the BE students. That's why this session will be very much helpful for all the final year students for doing their projects in simulation. And we have with us today Mr. Sandeep Hirde, who has more than 14 years of experience in the field of computational fluid dynamics. Okay, so whatever he is going to present today, okay, I appeal to all the students that you take the benefit, okay, of his session, because he is going to do some live simulation also, or he is going to show some live simulation also and on his in his presentation. So one case is also going to be handled by him. So I will ask our HOD Dr. VC Shewali sir to please proceed for introduction. Sir, please guide us.
Okay. Hello, I'm audible?
Yes. Yes, sir. You are audible.
Yeah. Good afternoon to all. On behalf of Mechanical Engineering Department, I welcome today's speaker, Mr. Sandeep Hirde, Siemens Gamesa Renewable Energy Bangalore, for the webinar on Introduction to CFD. Today, he will share his views on basics of CFD, CFD process, modeling, numerical analysis, CFD codes, and also he will share his views about the career opportunities in CFD. So this session will be very useful for the student who are interested to work on the project related to CFD. Department has already published the topic of project on Google Classroom for the final year student. So many topics are based on the CFD analysis. So I hope this session will be very useful for the student as well as for the faculty of our department. So once again, I welcome Mr. Sandeep Hirde for this webinar, and I request him to continue the session. Thank you.
Thank you, sir. And yeah, as sir has mentioned, CFD is now a growing field, and for past 20 years, it has grown to such an extent that most of the companies have shifted from the experimental or testing era to CFD era. Now, if we look about the process, we have lot of things to consider in the CFD simulations. So I will take you through all this, how to model physics, how to model geometry, what consideration we need to take, and what are the numerics behind any computational code. And then we will go through one simple example, and in your projects you might need to explore more and more. But if we see CFD, CFD is not just a software. Okay, CFD requires a lot of basic fundamental knowledge, and this fundamentals knowledge you have to gather from your third year of engineering. It is basically in the CFD, you have to consider heat transfer and mass transfer. Then you have to consider complete fluid dynamics, and then the heat transfer or whatever the physics that we are going to model in the software. This will be converted into partial differential equations, and then the partial differential equations will be solved with the help of numerical methods. So let's go and see what is CFD and what will be the advantage once you learn CFD, and what is there for you at the end of this session, how you can go in the market with the different career opportunities. CFD basically stands for Computational Fluid Dynamics, and the Computational Fluid Dynamics is a part of fluid dynamics where we use numerical methods to solve the partial differential equation. And this is the science of predicting fluid flow, heat transfer, mass transfer, any chemical reactions, and a lot of other things. So this is the science which is based on numerical and mathematical equations. And this is basically fluid and the energy, so heat transfer. So we have conservation of mass, the conservation of momentum, and conservation of energies. This is the basic three fundamental uh, for any kind of solution. And uh, we have to model these equations into partial differential equation. Once we do the CFD analysis, so which is relevant for any engineering data, so we do or we use CFD for conceptual studies in any new design. We use CFD analysis to develop the product and to troubleshoot any RCAs, root cause analysis of failures, and we redesign. So uh, in the industry where the CFD is used, there is vast uh, area where the CFD is used, and we are going to see where it is basically used. But before that, let's take a look at the advantage of CFD simulations. Why do we require CFD simulations? As I told that when we go for experiments, the experiments cost preparation of model, which requires a lot of resources, efforts, and then we have to go for any experiments. So let's take an example of aircraft. So for aircraft testing, it is not very simple to just build the aircraft and do testing. It requires a lot of time, lot of efforts, and lot of cost. So why CFD will give advantage over the experiment? Once you have a good correlated CFD model with the experiment and the test data, then the further simulations will have very low cost compared to test. So simulation is basically design instead of build and test. Simulation is also very fast. So uh, aircraft outer body simulation or wing simulation to predict drags and lift, uh, we have to do a test in wind tunnel, which takes building the model, and if we consider the time, it will require at least 6 months preparation. But whereas when you want to do a CFD simulation, you can finish that 6 months task in hardly 2 weeks. So that is the advantage of CFD simulations. So it is a quick turnaround for the engineering data, and it can be introduced early in the design process. So you don't have to complete your design and then go for test and then remodify based on the test results. So when you do CFD simulations, you predict, then you change your design, and that will be introduced early in your design process, and at the final you can do only one test to prove it. Simulation also will have a ability to test real and ideal conditions, whereas in the experiment it is very difficult. Some of the times you will not have experimental data, and it is very difficult to put a sensor at very difficult locations. So let's suppose if we want to simulate a combustion, whereas we cannot put a, thermocouple to measure the temperature. So in the simulations we can uh, you can predict that phenomenon, and you can have the results. So it is sometimes very beneficial where we cannot use experimental sensors. Also we can do any scale simulations. So based on the full scale model which we do, generally the test will be happen on the scale simulations or the scale models. But whereas the simulation can be done on any scale, simulation has an advantage to do uh, simulations in hazardous conditions like explosions, radiation, pollution, whereas it is very difficult for test to measure all this data. And lastly, the simulation will be used for comprehensive information, whereas we have a lot of data, a lot of variables which can be predicted from the CFD simulations, and this can be used to explore the flow physics for the given problem. So where simulation is used, there are numerous fields where simulation or the CFD simulation can be used. The main CFD started from aircraft or the aerospace industry, but nowadays the CFD is used for all the area. So if we see aerospace industry, we have lots and lots to predict: the drag, lift, then the engine cooling, inside air ventilation, passenger comfort. So all this can be predicted using CFD. In the automotive domain, we can have uh, flow over the car where we can predict the drag, and we can modify the design, and we can reduce the drag so as we can increase the fuel efficiency. We can also simulate the combustion, the NOx oxidations, and the external or internal aerodynamics in the automotive and aerospace industry. In power industry, we can simulate the steam turbines, the generator coolings, wind turbines, where currently I'm working on the wind turbines, aerodynamics, internal cooling, tower cooling, nacelle cooling, panel cooling. So there are lots and lot of area where we require CFD to predict the result before the test. And we change the design based on the CFD and then redesign. And at the end, we just verify the CFD simulations and with the test, and then the test will be in one go, test will be passed. So these are the few examples. Let's see the other industries. We can use CFD in HVAC industry, where we use CFD code to understand the heating and cooling of the building, the ventilation design of any big tower building, electronics cooling, where we can predict heat transfer for the electronic packaging application uh, from small scale to large scale. We can use biomedicals. We can use CFD in biomedicals, where we can have the prediction of blood flow in the heart, in liver, in all your veins. So in biomedicals, again, any equipment design for any industry which has heat transfer and fluid flow phenomenon, we can use CFD to predict and design the equipment. If we see the industries, we have a lot of industrial application where we predict flow and heat transfer in the industrial process. We can use CFD for predicting boilers, heat exchangers, combustion equipments, pumps, and blowers performances. So all this will be used to either increase the heat transfer, to reduce the pressure loss, to reduce the drags, and to increase the performance. Even in oil and gas plant, we can have drilling. So in that condition, how the flow is happening inside the drilling, and how whether we are getting sufficient oil, or how the flow is getting uh, over the plant, because the plant is situated in the sea, and there should not be any extra forces coming on the plant, oil plant, and it should not collapse. So these are the different areas where we can use CFD. In the marine industry, we can use CFD to predict drag over the ships, and to design the ships in order to reduce the fuel consumption. In the chemical, where we can use CFD to predict the heat transfer for any reactor vessels and flow separations. In the sports, you can also use CFD for coaching, uh, equipment design, then the play techniques, and there are many numerous examples. Let's look at the CFD process, how we have to do any problems solving. So we start with definition of the problem, then we try to model the problem, and then solve, and then post process. In the first early stage, one has to be very sure about definition of the problem. What is the real goal and objective of the CFD simulation? Because your total CFD simulation is based on your problem definition, and you have to first define what is required out of the CFD simulation. So define your output, and then based on that, you have to model completely your problem. So let's take an example where you don't want to model the heat transfer. Then in that condition, you have to define your problem only for the flow analysis. So that's how you define your output, and then based on that, you start your modeling. In the modeling, we have a different flow, whereas we start with the geometry. So for the complex geometry, we have to use CAD software, then clean the geometry, and then use that geometry, define the domain size, and then model the physics. So geometry preparation is the first important step in any CFD process. Uh, your results will be based on your geometry preparation. Now we will go in little bit detail how we have to consider the geometry, how we have to consider geometric parameters, how you have to consider and define your domain and domain size. And once you are done with the geometry, then we go for physics modeling and meshing. In the physics, now we have lots of parameters to consider. We will see how we classify flow, and might be you also know how the flow classification happens. So based on that, you have to consider the uh, physical model. So if you want to solve heat transfer, you need to consider whether the heat transfer is on or off. If you are modeling compressible flow, then your domain will be different. When you are modeling incompressible flow, then your domain will be different. When you are modeling oil, then your domain will be different. When you are modeling, so it is like your uh, physics will be governed, uh, and the geometry will be governed by physics, and then the physics will be governed by your problem definition. So what you need to solve, and then once you have your total physics defined, then you consider this physics into your geometry, define your geometry, and then go for meshing. So in the physics, you have to consider what is your input data, whether you have sufficient inputs, that is your boundary conditions. And then when you start your solving the problem, now the partial differential equation, when it is converted into numerical form, it requires the initial conditions to start with. So initial condition is nothing but your just a guess. Now the initial conditions are also governed by or can be derived from the boundary conditions, or you can provide any initial conditions for the solution, and then the iterative process happens, and then when the simulation or the solver solves from the initial condition, it will be iterated, and then you, at the final you will get a solution. So that is how your initial conditions will be uh, when you define proper initial conditions, the convergence will happen faster, and then the solver or the solution will be you will get solution early. Then you once you have a mesh, once you have a geometry, you go for meshing. Now meshing, you can go for unstructured meshing or structured meshing, and for both you have automatic approach or manual approach. In the automatic approach, you may not have control over all the parameters, but in manual approach you can control each and every cell, and you can define your mesh. So this is about the modeling. Once you are done with modeling, you have to solve. So once now in the solver, you have to define your problem, whether it is a steady problem or unsteady problem. Define the iterations per step, convergence limit, the precisions, and the main thing is you have to choose the correct numerical schemes. So the numerical schemes will again be there are some schemes which is applicable for some type of problem. So it is very much important that you choose the proper numerical scheme, you choose the proper turbulence model, you choose the proper settings of the solver, then you will be getting your solution very fast, and your solution will be converged. If you have anything wrong, your solutions will not converge, and you will get errors, and the solver will come out without giving you the solution. So let's suppose you are done with all the first three steps, then you go for post processing, where you have various tools to extract the data from CFD simulation, and then uh, you verify the results. Again, the results will be based on what physics you have modeled. So if it is not correct, then you have to go again back to the modeling, change the physics, and again rerun. So this is how the process is. It is bit complex process, and each and every step is very important. So let's just look into a different bucket here. Okay, and we will just have a look, and then we will go for problem solving. So once you once you have a problem, you define your problem, then go for the geometry. In the geometry, you can create geometry in CAD when you have a very complex geometry, or the designer will be different. You get that geometry from the designer, which will not be suitable for the CFD analysis. Then in that condition, the geometry will be simplified, and then you have to create the CFD domain. Now, the typical approach is like you use CAD and CA integration tools, and then there will be a transformation of geometry from CAD to CFD, and then you have a three coordinate system to choose from: Cartesian coordinate, cylindrical coordinate, and spherical coordinate. So either one of the system or your model will be fit in one of the systems, and you can model and you can use that system or use that coordinate system. So once you mesh it, your partial differential equations will be again transformed from any one of this system to general orthogonal coordinate system, which will be used to solve any numerical problem. So when you get the geometry, which will be very complex, let's suppose. Here you can see you are modeling any steam turbine and generator, so you will have lots of components. Then in that condition, you have to consider what is the goal of analysis and how you define your domain. So you define your domain based on what is your area of interest. In that, again, you identify the different components of the model. In that, you will have focus bodies, the necessary bodies, peripheral bodies, dispensable bodies. So these bodies is nothing but in the focus bodies are the greatest, you have a greatest interest on these components. Necessary bodies is nothing but these bodies can affect your flow physics or the heat transfer, so it is a necessary body. There are peripheral bodies which have uh, either influence or it will not have an influence, but you are not certain. So in that condition, you can keep those peripheral bodies in your simulation. There are dispensable bodies where you can see that these bodies, if I remove from the CFD domain, there won't be any impact on the results. So you have to remove all those dispensable bodies from your CAD model in order to get a clean CFD model. And I have shown how the iSpec is used in the electronic simulation. So where you can see a panel, and this panel is converted into a iSpec model, and then we do a simulation only on the focus and necessary and peripheral, only three type of bodies. We don't consider dispensable bodies, and we also defeature the geometrical details that do not affect the flow and heat transfer physics. Now if we consider the physics, I have shown only two main areas, heat transfer and fluid dynamics, but CFD can be modeled in other areas also, and we have to accordingly consider the appropriate physics. So in the heat transfer, whether your heat transfer is happen because of the conduction, convection, radiation, then in that condition you have to appropriately switch on the physical model in your CFD simulation. So consider you don't have any radiation, then you don't have to solve the radiation equation in your CFD simulation, because solving radiation equation take longer time. Again, if you have only convection or conduction, appropriately you can switch on those model and rest you can switch off. When you have any type of problem, that can be again divided into inviscid and viscous problem. So again, inviscid have incompressible, compressible, internal flow and external flow. Viscous also have laminar and turbulence, and then again this laminar and turbulence again have the four types. So that's how you arrive your physics, and then appropriately you can switch on the models. So once I open the solver, I can show you where are all these options available in the software, where you have to choose appropriate turbulence model. If the turbulence is not present in your physics, then you have to switch to laminar, or whether you have to solve compressible flow or incompressible. Then based on the external or internal flow, again there are some settings like your time step or the velocity. Based on the velocity field, for internal flow it is different, for external flow it is different. Then your turbulence regime will be different for internal flow and external flow. So all that you have to consider. So in CFD, you should be thoroughly able to understand the physics of the problem. So there are different types of turbulence models, and based on these turbulence models, you solve your Navier-Stokes equation. Now we'll go to Navier-Stokes. What is Navier-Stokes equation? So basically, if you have learned about fluid dynamics, or if you have not yet, then you go and understand what is your three basic fundamental equations for the flow. So conservation of mass, conservation of momentum, and conservation of energy. And the conservation of momentum equation uh, gives Navier-Stokes equation. So based on the conservation of momentum, uh, the Navier-Stokes equations are derived. So these Navier-Stokes equations are solved by different turbulence models, and there are four types, basically DNS, RNS, LES, and DES. So basically, you will have to resolve the turbulence flow, and these are the four different methods. Uh, Now, we'll not go through in detail this, but these are the different methods. Again, in the RANS method, so RANS method is nothing but Reynolds average Navier-Stokes equation method, where we have again different types of turbulence equations, K epsilon, K omega, SST turbulence model. So these are the industry preferred turbulence model. Generally in the industry, we use this kind of turbulence model to resolve the flow. The next step is the grid generation or mesh generation, where if we consider any flow equations which are uh, derived over a control volume. So this control volume, now we have a geometry. We need to have a control volume and different control volume in your CFD model. So what we do, we discretize the domain into finite set of control volumes, and then these partial differential equations are derived over this each and every node, and then this will be solved through numerical equations, and then we arrive the solution. So we have now two different types of approach: the finite difference for the structured mesh, and finite volume for the structured or unstructured mesh. And now for resolution of any boundary layer, we have to put the fine mesh near the boundary. Now you have you are seeing the aerofoil, where we try to find the flow behavior near the aerofoil. So we have to have good mesh in and around the aerofoil. So this is how you mesh it. You have different types of elements you can go through: Tate, hex, pyramid. So there are a lot of different types of elements for the unstructured mesh. For the structured mesh, you have only hexagonal element, and then you have two different types of meshes, again 2D and 3D. So you define your problem whether it is 2D problem or 3D problem, and based on that we have to discretize the domain. Now in the solver, we can have different types of solvers available. The uh, trigonal or penta diagonal solver, or solution adaptive solvers, multi-grid grid solvers. So we can choose from the drop down menu in the solver, and we can use. There are different numerical methods also. So once you decide to learn, then you have to learn all these numerical methods, which are iterative methods, and these are like Gauss elimination method, or Jacobi's method, or Gauss-Seidel method. So these are the methods on which the partial differential equations are discretized and then converted into linear algebraic equations. And then these linear algebraic equations are solved with the help of iterative method. And in order to get the good convergence, and we have different controls for the numerical parameters, which we called under relaxation factors. We define the convergence limit, then different numerical schemes like forward difference, backward difference, central difference, So these are the different numerical schemes we have to choose, and then you define your number of iterations for steady flow, or you define the time step for unsteady flow. So once we go through the solver, actual solver, we will go through all this. This is how your partial differential equation is written over the control volume. The first equation shows it's a continuity equation, which is conservation of mass, and then we have three equations, which is three momentum equation in each direction, and we have local acceleration, convection, then pressure gradient, and viscous term. So whenever the flow is passing through any control volume, we will have these four kinds of terms, and based on these four kinds of terms, we write the momentum equation. There will be again energy equations, which I have not written here, but when you are trying to include heat transfer into your fluid phenomenon, then again the energy equations will be solved. We'll just have a glance over the finite difference method. So there are three different finite difference method: forward difference, backward difference, and central difference. And this finite difference method will be based on your grid. So let's suppose you have a node where your suffix is I and j. Then if you want to calculate any variable here, let's say you are calculating velocity. Now this will be based on uh, the front and back nodes, and then you write your equation for this node based on this velocity based on the Taylor series. Now this is the Taylor series, and then you have a differential velocity in x direction, y direction, and if it is a 3D problem, you will have in z direction. Then you have the finite difference representation here, and based on that finite difference representation, either you can choose the forward method or backward method or center method. So it is based on you. And then we will have a truncation error. So truncation error is nothing but you don't consider the higher order method, higher order for the uh, partial differential equation. Once you have a solution, then you go for post processing, where you visualize uh, all the data. So from that you see whether your overall flow pattern is correct, is there any separation, then what is the flow features that we intended to resolve, and all this can be seen through vector plot, streamline plots, then animation, 2D and 3D contour, and then this is just a visual graphical representation of the data. But when you want to extract data, then you can extract data for there are number of variables for which you can extract the data, and you can have xy plots, vorticity, wall shear stress, forces, movements, pressure, temperature, velocity. You can calculate your own variable like lift, drag, torque, then heat transfer coefficients. So this can be calculated from the solution, and it has to be from the converse solution, the mesh independent solution. And then once you are done with that, you verify your data with the test, you verify the computation with some small hand calculation, because there are chances that because the CFD process has different variables and you never know where you are going wrong. So always the CFD simulation has to be verified and validated either with the test data, the hand calculation, or with the experts. So this is all about the CFD process that we have seen, and I would like to uh, this we will see later. There are different CFD codes in the industry: Fluent, Star CD, CFD RC, CFX. These are the commercial CFD codes, and then there are research CFD codes, and then you can also have free CFD codes where you can download from the internet and do a small calculation by yourself. And there are other softwares which are required to support uh, for doing any CFD calculation, like the grid generation software, where we need to define or discretize your domain into small control volumes. So we use ISM CFD, CFX Measure, Gambit, GridGen, and we have post-processing softwares. Now there are TechPlot, FieldView, CFD Post. We can also use Fluent for post-processing, CFX for post-processing. So these are the CFD codes. Now, guys, uh, we'll take this later. We'll go uh, to solve. We are going to solve a just simple problem where we have a cylinder and there are different flow regimes when the flow is over the cylinder. When the flow is laminar, you can have a small pair of vortices. Then when the as the Reynolds number increases, your flow is getting separated and the vortex shading start. So basically this is the physics and we are going to model it. So we are going to define the domain where we have a cylinder, and then we define the domain, fluid domain. So this is called upstream, where we have upstream data here, the downstream, because the flow is coming from the inlet. This is the downstream. And then we have symmetry boundaries on top and bottom. So now we are going to solve just a 2D problem. I will show how the 2D problem need to solve. I'm going to use ANSYS. Now we have basically CFD in any industry. ANSYS is the most preferred software. So you drag geometry. This geometry has to be meshed. So you drag the ISM CFD, and once you mesh the model, you either solve it in CFX or you can solve it in Fluent. Now, once you have a geometry here, either you can import geometry or you can open the space claim here and create your own geometry. So let me import geometry. Okay, so I have geometry. Let's verify it. Okay, so for anybody has any question?
Yes, if anybody is having any query, please you can write in chat box also, or if you feel that you can ask online also. I think first let us finish this, then we will have some questions.
Yes, yes.
Okay.
So yeah, so I'm going to now this is my geometry. Let me, okay, this is 100 mm, and then I have uh, the outer domain where we have the upstream, downstream, and above and below CFD domain. So this geometry is transferred to a meshing software where I would like to mesh this and give the boundary conditions based on the requirement. So okay, so I have my geometry here. Okay, now what do? You you build the topology. So what happens when you generate any geometry which may not be suitable for the meshing? So you build the topology, and based on the topology, you will be able to mesh the model. So now your geometry is ready. So before that, let's define the inlet. Okay, so I will switch on the surface. Let's define inlet. So this is my inlet surface. Then outlet. This is where the flow will go out. And then cylinder. So this is the cylinder. Then I should have symmetry boundaries. So top, bottom, and front and back. So these are the symmetry boundaries. So here I give name so that the mesh will understand that these are the region or these are the cells face on which there will be a boundary condition. Otherwise, the code will not understand uh, and it will not be able to iterate. Okay. Now I start meshing. So you go for either tet mesh or hex mesh. So let's go for a hex mesh. You define the 3D block. So if you, so this is my block where I would use hex blocks to create the mesh around the cylinder. Now here we have circle and here we have a rectangle. So here I would like to create O grid. So there are different types of grid topologies that you need to understand. C grid, O grid. So these are the types of grids you can use. I would like to create O grid here. So I create O grid. So the grid lines will be, once I mesh it, grid lines will look like here, and then there will be grid lines coming from this side. It will have angle, then go straight, again diverge. So it's a kind of O grid. Now the hexa sides of a block has to understand that I have this edge, it has to take a shape of this edge. So we have to associate this edge to the curve. So I select these four edges and then associate with these two curves. There is one option called project vertices. So once I select that, it will try to project on that. So it will project. This is how it will project. And we have to also project these four faces, four vertices. So I will move these. And in order to have good quality mesh, now this is, I'm doing it manually so that I will get good quality mesh. Now your blocking is done, and this is not the flow region. So what I will do, I will delete the central block, so there will be no mesh in the central block. Then I define the number of points. Okay, so define the mesh parameters. And here you copy this parameter to all parallel edges. Let's say I need 20 cells. 20 here, and another 20 here. Then on this 25, 20, and let's say 50. So just switch on the pre-mesh. You will be able to see how the mesh is. Okay. Now here I forgot to give the number of elements. Then I select here, and let's say 25. Okay. And here you look, the grid is almost uniform grid. Okay. Then now let's resolve the boundary layer around the cylinder. So how do you resolve the boundary? You select the edge which defines this, and then here is the arrow from which this edge start. So you can have a spacing defined for the second one. And then give a growth ratio and check. So now you can see here, your first node will be here. So that's how you can check it. Again, pre-mesh. Okay. So here you can see you have smaller cells here around the boundary, and then you have growth. Now let's check the quality. So here you go and check the quality. Now here quality is more than 0.6. So it's good, but still because this is very simple mesh, you can go for higher quality. Also you can define in the Z direction or the Y direction. Now I'm just trying to solve 2D problem, so I would like to have only one element here, and then on the edge also go and try for auto association. Okay, so now you have little better mesh. Still you can, so there is some problem here. Let's fix it. So once you're done with the mesh, you save your mesh. Before that, you convert into, write the file and select the solver from here and just click. First you save it, save the project. So your meshing is done. Now you put that meshing into CFX and open the CFX pre. Okay, so this is how your geometry will be imported here. You define your domain. Okay, then you select. Okay, so now what I was talking about physics. Okay, how to model it appropriately. So here you will have the material library, the domain type, whether it is fluid, solid, porous, or immersed solid. Now when you are modeling any porous media, which is like a filters, so you have to choose porous. When you are trying to model the heat transfer with solid interaction, you have to choose the solid domain. So in a model you will have fluid and solid domain both, or you will have the combination of all these. So based on the appropriate, you can select. Then you have the option to use the fluid. So here you will have material library, or you can define your own fluid, and then you can uh, give the properties. So now here you can see air at 25. Now that will be in your library. So this is the library from which the material is used. You can define your own material. Okay, so once you define material, you give your name, and then once you give, you will have to choose the different properties. Okay, so there are a lot of properties you can define based on whether it is generic material, specific heat. Okay, all those properties will be given here, or there is other option to choose from the given library. So let's say you are taking the material from the library, then whether it is continuous fluid or dispersed fluid, so you have different types of again options to define. Now the flow over cylinder is a continuous fluid. Now define your domain model, the pressure, whether buoyancy is applicable, whether it is buoyant flow or non-buoyant flow, then whether it is stationary domain or rotating domain, whether there is any mesh deformation you require. So it is like you have some options to choose. Then there is a fluid model. You have to either choose the heat transfer, or it is isothermal where you don't have heat transfer. So you have again three options, four options: isothermal, thermal energy, and total energy. So based on that, you can, in the total energy, you can include the viscous term if it is a viscous flow. If it is not, you can go for only the thermal energy, or the isothermal means there is no change in the heat transfer. So all the properties or all the calculations will be done at 25 degree. Then whether you have turbulence region or laminar flow or turbulence flow. So if you say there is no turbulence, you choose laminar. If it is turbulence, then you have four options: K epsilon, SST. So based on that, you can select your turbulence models. Then based on the turbulence model, you have to choose wall function. If it is a combustion problem, you can check it. If it is thermal radiation option, it is present in your physics, then you can choose it from here. And then you initialize your domain. So this is how you define your problem. So let's say in this problem, we don't want to solve any heat transfer. It is isothermal problem. Let's say it is a turbulence region, and there is no combustion, there is no radiation. You define your model, initialize domain, then initialize with the initial conditions. So initial conditions will be chosen from the boundaries, and it is automatic, or you can give automatic with value. So based on the values, it will be initialized. Otherwise, you can have automatic initialization. Pressure, again, it is automatic or automatic with value, and the turbulence. So once it is done, you define your domain. Now in this domain, you will have some boundaries from where the flow is coming, one boundary from where the flow is going, other boundaries is symmetry, cylinder is wall. So you have to define all those boundary conditions. Now you insert boundary conditions, let's say inlet, from where you will have flow. So the boundary type, you will have different boundary types here, inlet, and then you choose your location. inlet location. Then the boundary details. Let's say the velocity at the inlet boundary is 10 meters per second. Then based on the velocity, you will have your Reynolds number calculation. Then if you have any boundary source, so these are advanced options. Then I define outlet boundary. Then at the outlet, what is the boundary condition? So I have, let's say I define my relative pressure as 0. Then I have cylinder, which is wall. So I define cylinder as a wall and no slip wall with smooth option, or you can also have rough option. And then you can define symmetry boundary. Okay, so I define all my boundaries here. Then you can go for analysis type. So analysis type, whether we need to do a steady state analysis or transient analysis. So we'll just go for the steady state. Then the solution units are defined here. Okay, so all these physics or the numericals where we have to choose the different schemes will be in the solver control. So in the solver control, you have advection schemes, the turbulence numerics, whether it is first order or high resolution, then the convergence control, so where you can define your number of iterations. So let's say, so this number of iterations will be at the end of 200 iterations, the solution will be stopped. Or you have a convergence criteria. So let's say you have RMS convergence or the max convergence. So this is the residual type. These are once you read the theoretical information about what these controls are, then only you are able to understand how to change and what to change. So once the convergence criteria is reached, the solution will be stopped. Otherwise, the solution will be stopped on the given number of iterations. Then you will have the time scale definition here. So where you choose the appropriate time scale or auto time scale, and then you define this. Again, you will have advanced control for continuity equation, momentum equation, and the turbulence. And there are again different controls where you can control the uh, solution of algebraic equations. So for the basic, I think you should not go through second and third tab. This is the controls you can define. Then you can define the output controls where you require to have extra variables. You can define it here. You take a backup after some iterations, so you can define the backup, let's say after 50 iteration. And then you define the monitor points. You can define monitor points, monitor particles, residuals. So there are lots and lots of options when you want to define. So then you can go for simulation controls. You also can write your own expressions here. So you can insert expression, and that expression you can call in your simulation here. So there are lots and lots of controls here. So almost my problem is defined. I save my problem here. And then I solve it here. So once the solution is done, we can do a post processing for the simulation. So I think it will take a couple of minutes to solve because it's a simple problem. But for the complex problem, CFD takes almost, based on the computer resource, it will take many days also. So if you have high computing power, you can have a complex. There is some error I might have missed. Then you can open and you check. Okay, so there is some problem in the checking, mesh checking. Uh, so let me just quickly open which I have already solved it. Okay, it is, this was not converge, so I'll close it. Okay, anyway, for demonstration, I think I can show. Okay, so here you can see how when there is a flow. Now this is not a converse solution, so you always should have a converse solution for the post processing. You can see from here, and then you can extract the data. But there are various options to uh, post process the simulation. Now I have created a plane from the center of the domain here, from the center, and I, so there you can plot the variable on the plane. You can plot velocity, you can have pressure, you can define the range, or you can have global range. So once you see, this is not the converged solution, so you see it, there is no pressure change, but in reality you will see, or maybe it's better that I will open the converged solution. Okay, I think I, anyway, I was just trying to show you. So you can have a lot of variables here. You can also have streamlines, the vector plots. You can select the plane on which you would like to have the velocity vectors. So this is how the flow will be. Let me just open the appropriate case. Yes. So here you can see how the vertices are. There is a flow separation here, and then the flow recirculation. So this is how you can post process it. When you plot the velocity, you can see how the velocity is along with the vectors. You can have pressure plot. So you can see how the pressure is developed. Here is a stagnation point, then the flow acceleration, and then the flow recirculation. Okay, we'll go quickly over the limitations of the CFD. We'll have the limitations in the physical modeling. So there will be a human error, there will be a numerical error, the round off error, the truncation error, and when you put wrong boundary conditions, you will get wrong results. So it is always necessary for every CFD engineer to understand the physics properly, to model the appropriate physical model like turbulence, the compressibility, multi-phase, chemistry, heat transfer. So there are a lot of things we need to consider. And when you are solving, you need to choose the correct numerical scheme so as to reduce the numerical errors. Uh, so it is very much important that CFD is just a tip of the iceberg, but whereas you should have the knowledge, the basic fundamental knowledge of fluid mechanics and heat transfer, the mathematics, numerical methods, and then based on all these three, the CFD will be uh, your, tip of the iceberg. You will have a lot of career opportunities in CFD. Uh, there are two streams basically, the code development and the industry opportunity. So in the code development, people who have more knowledge on the mathematics and numerical schemes, they can go for the code development where you need to understand and you need to convert the mathematical partial differential equation into computer codes. And in industry, you use CFD applications or CFD softwares. Based on your fundamental knowledge, you solve the industry problem. So you have more opportunities in the industry compared to the code development. Here are some of the reference books which you can use. So I will forward this presentation to your corresponding teacher, and maybe you can get this presentation from him. So thank you for listening me, and thanks for the opportunity to present. So if anybody has any questions, please let me know.
Yes, yes. Thank you, Sandeep. It was a very nice presentation, basically. Uh, may I request from the participants, if you have any question, please post your query in chat box, or you can ask personally also. Before that, I also want to ask some of the questions. Okay. If,
Yes, yes.
if anybody from participant want to ask, please ask, or otherwise I will ask. Okay. Sandeep, sir, you have mentioned the convergence of the solution. Okay. From
Yes.
from that particular results, how will we come to know that the solution is converged? So what is the criteria to select whether our solution is converged or not?
Yes, basically, in order to see whether your solution is converged or not, your residual error should be less. So that is the
Hmm.
first criteria.
Hmm.
How do you select the residual error? So when you go for the solver, in the solver you will have a residual error mentioned. So if the residual error, your criteria is less, your residual error is less than your criteria, your solution is converged. That is one way.
One.
The other way is, now here I can show you in the solution yeah. So here you have a residual target, okay, and residual target is your RMS of any variable, okay, basically mass and momentum, okay, because you are just solving the flow simulation. So your mass and momentum RMS is less than your residual target, then your solution is converged. This is first one. The second, you can put the monitor points in your simulation, and you can check whether the monitor point shows the steady variable in your solution. Okay, so this is second. And third is, even if you have monitor points and the simulation is unsteady, you will not get convergence. So then you need to see whether your physics is correctly modeled or not. So you basically you will have uh, the variation. So I can display uh,
Monitor.
monitor. So let me just open the solver. Okay, so now you can see here. Okay, so this is how you can see whether your solution is steady or it is having lot of oscillation.
Variation.
Okay, so this solution is not converged. This just I started 5 minutes before, and it was not completely converged. So you can see. So this is one way. The other way is you can put a number of monitor points and you can check. And now the flow over the cylinder is not a steady phenomenon. We are solving this as a steady phenomenon. Basically, it's a transient
Steady.
phenomenon. Okay, so however you change the controls here, you will never see a steady residuals, because the physics itself we are modeling wrong. We have to solve this problem with the transient settings. So that is how, where you can change your analysis types and you can change to transient, and then you can control your and you can have the oscillations, and you can have time variation in your solution.
Okay. Okay. Thank you. One more question I want to ask.
Yeah.
You have mentioned a parameter called quality. Okay.
Yes.
That where some number, it was 0.6 you have mentioned. But
Yes.
how will we come to know whether it should be 0.6, or means what is the range that is giving us? Means what should be the value of quality for getting
Okay.
better results?
So for simple geometries, you can achieve quality more than 0.9. But when you have very complex geometry, for good solution, try to achieve a quality more than 0.4, more than 0.4 or 0.5.
Okay. So maximum value is
Yeah, maximum is 1.
okay.
But yeah, when you have complex geometry, you will never achieve more than 0.5.
Fine.
So
Okay.
at least if you try more than 0.34, then also you will get a solution. In case of
Okay.
unstructured hexahedral mesh, okay, now we are using hexahedral, but in case of tetrahedral, then quality will be very less. Quality will be like 0.1 or 0.2. So in tetrahedral, if you try to achieve a quality more than 0.2.
Okay. That means it depends on that meshing also.
Yes, yes,
Whether it is tetrahedral or hexahedral.
right, right.
So means it might be depending upon the type of problem. Okay, whether we are going to use tetrahedral mesh or hexahedral mesh.
Yes, yes. So based on the complexity of your geometry, you can decide whether you have to use tetrahedral or hexahedral mesh.
For solving the simple for students, for solving simple
I
cases,
think
we can go for simple
I think
tetrahedral.
for yes, you can go for tetrahedral, but for good quality, I always try to go for hexahedral.
For boundary layer and all that, you have to use
Yes,
hexahedral.
yes. Even tetrahedral also you can have a boundary layer. There is no issue.
Okay. Okay.
Yeah.
So
So there was
the
yeah.
question
So
here. Hmm.
here you can see, here
Okay.
you have a hexahedral. Here you have a tetrahedral.
Okay. 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 Our professor, Dr. Sonone, he is asking
Yeah.
why simulation showing reversed flow in turbulent flow problems? Reversed flow.
Yeah, basically, if you see turbulence, the turbulence is nothing but uh, you have a disturbed layer of flow, and
Okay.
sometimes when there is lot of turbulence, you will have a small eddy scales which is developed in your flow, and then you will see a small reverse flow. But in general, there will be uh, flow physics where, let's suppose, there is a flat plate with a back step or front step. So in that condition, you will have a region where the flow will not go, and in that condition, your velocity and pressure is very less. So flow will have a reversible phenomenon. So in a problem now, I was showing here, right?
Mhm.
Okay, so here what happened, your flow is accelerated over the cylinder, and then the flow is detached from here, and then flow will go like here, and here you will have very less velocity and less pressure, and then the flow is reversed here.
Reverse. Yes.
Yes,
Recirculation. Yes.
recirculation.
That is the boundary layer separated. Okay.
Yes.
Okay. Okay.
Hello.
So,
Hello, Mr. Sandeep.
Hello.
Yeah, yeah.
Yeah, oh, my one question is that in CFD we need to specify the boundary conditions, right?
Right.
Yeah. So, is there any standard procedure to specify the boundary conditions?
Yes, basically, the boundary conditions will be like you will have first class boundaries, and the basically what happens, there are class of boundary conditions. Maybe you can go through the literature. So there will be a confined problem, and then you will have inlet mass flow, outlet pressure. So this is called the perfect boundary conditions problem. So that is how you have to choose your boundary conditions, and boundary conditions are also again based on the information available before you are solving any problem. So let's suppose now you know that your flow incoming is at some velocity or some pressure, so based on that you can choose that boundary.
Okay, okay.
Yeah.
related to this boundary, means suppose at inlet condition we know the boundaries,
Right.
and at outlet condition, suppose we are normal whatever you have mentioned, just outlet pressure. So whether it is taking automatically solving that conservation equation.
On the outlet boundary, we are just mentioning that the relative pressure is zero. So when the relative pressure is zero, the pressure built up will be based on the zero outlet pressure. So it will be reverse calculation.
Okay, okay. The drop will be taken into account.
Yes, yes.
Whether we should put actual condition at the outlet, suppose there is vacuum at the outlet, then whether we should provide negative value for pressure
If you
at
have
outlet.
information, you can put.
Okay, okay. Yes, Kushare sir, you want to ask question?
Sir,
Yes,
I
yes.
have one question.
Yeah.
Hello, Sandeep sir.
Yes, yes.
Uh, I have one question. I'm dealing with the hydrodynamic journal bearing.
Okay.
So my problem statement is I am finding the properties, static and dynamic properties of the bearing. Okay,
Mm-hmm.
so I am dealing with the surface of the bearing. Okay,
Okay. Okay.
so I'm solving that by using the analytical softwares that MATLAB and Fortran.
Mm-hmm.
Okay, so but I would like to that simulate that in the CFD.
Okay.
So my problem is that so basically I'm working on the surface, that the
Mm-hmm.
bearing surface, and that surface is a microtexture.
Okay.
So can we simulate in the CFD that problem?
Uh,
So initially, see, I have to compare the properties for the plain bearing and the textured bearing.
mm-hmm.
Okay, so I'm using the micro texturing for the surface. Okay, so
if you have a surface roughness for these two specific bearings, you can give the surface roughness and one is smooth, or maybe two have two different surface roughness. Then you can compare the results.
okay, sir, but I'm using the different patterns for the surface roughness, like spherical or square or rectangular or different types of patterns, sir. So can we simulate that?
If it is very small and I
Yes,
think
these are the micro textured pattern.
I think it will be difficult because uh, its texture will not be, you cannot mesh those kind of things. And once if you don't mesh it, your solution will not capture it.
Okay, okay, okay. Yes, sir. Yes, sir. Okay, sir. Thank you.
Yeah.
So one student is asking, sir,
Yeah.
is it possible to solve a PDE, partial boundary conditions? I don't get this question, but is it possible to solve a partial differential equation with elemental boundary conditions?
Yes. Partial differential equation are basically is transformed into analytical equations based on the your grid. Okay,
Hmm.
so when you see your uh, grid or domain discretize, then you convert this partial differential equation into analytical equations. So for smaller domain, or for elementary is nothing but you just convert this domain into a small rectangular or elements, and then you convert this partial differential equation into analytical equations.
Okay.
Yeah.
Okay.
Okay.
So I think uh, questions are, there are no more questions now. So let us move towards the concluding session of today's webinar. Okay. So let me thank to Mr. Sandeep Hirde, sir, for sharing the insights of CFD with our students. Definitely, we have got the deep knowledge of simulations and its importance in an industry as well as in education field also. I thank to our management, Principal Dr. N.S. Patil sir, to Vice Principal Professor N.B. Desle sir, and our HOD Dr. V.C. Shevale sir for their support and valuable guidance for this webinar. I also thank to Professor R.S. Thakre sir for the technical support for conducting this webinar. Last but not the least, I express my gratitude to all the participants present for this webinar. Hope all of you might have got the glimpse of CFD from this webinar. So I appeal to all the students to go through this emerging area, which is very much required now in the industry for the current situation. And it will definitely help for shaping your career also. So you take interest in that. So I thank to one and all. Okay, thank you, Sandeep, and thank you all. So I declare that this session is over. Thank you.
Thank you, Satish.
Thank you, sir.